All right, so we're going to be graphing the sine function. Yep, let's make sure that you guys get all the notes for what we're going to cover here. Big thing, when you're doing your sine function, okay, this is the traditional sine function that we're going to be graphing. If they're going to mess with it, if they're going to put numbers in here, this is how they're going to mess with it. This is how they mess with it, for us today anyway. That they would throw a number out front, either adding or subtracting it. Hey, let's stop talking. Okay, the A number out front of the sine will affect the waves itself. The B number on the inside with theta will affect the angle itself. So I'm going to show you, as we mess with our function today, the sine function only, we'll do cosine and stuff tomorrow. When you throw numbers in here, it definitely dramatically changes this problem. Okay, the goal this week is to learn how to graph all the trig functions, not just sine, but do cosine, tangent, and the reciprocal functions. I know the first day, like yesterday, we just kind of intro this, what it is. I talked about some very generic topics that we can use this for, oceanic studies, for like tsunamis and waves. We talked about music, you know, with guitars and actual like symphonies. The goal today was to show you a video. I'll probably stop the camera at that point because it's a copyright infringement. So, I'll show the video of the actual wave of a guitar strings, so you can actually see that we can actually put a function behind it. We'll talk about the symphony itself that was created by just using triplets in math, where they do octaves and they do harmonies, and so it's very, very pretty music when you see it today. And I wanted to show you that just so you can see kind of the idea that it doesn't always have to be like engineering or math related like subjects, that we can go into like music and some other kind of cool ways to actually see this math that's involved here. But anyways, this is our goal today. If we can get this done tomorrow, we'll go into the cosine function. Now, as I said this week, we're gonna get another assignment, but it's gonna be kind of weird. I'm gonna stretch it over a couple days where I add just a few problems each day, not like a big mass like that, where I'm gonna do like maybe 3 problems tomorrow. Then we'll add maybe 3 problems Thursday, and a couple more problems Friday, and that's one assignment. We'll just have it in one. The reason why is I want you just to focus on one type so you're not confusing yourself. Does that make sense?
Yep.
Okay, but this is our first type. This is what your first 3 problems will be in the homework, and I'm going to try to give you kind of a range of problems where you have to test your ability on this. Tomorrow will be kind of one of those days where I want to see, can you actually do it by yourself? So I'll do a problem where I put one on the board and I'm going to have you try it. Today is the day we get all the shortcuts. So let's walk through this. Let's do the normal sine function, because we're going to mess with this one today. So this is the traditional sine graph, that you draw a normal coordinate plane where one of the sides is extended further, usually the right side. This is one snapshot. Now the book will ask you to draw two period lengths. I'm going to only require that you draw one, so you can actually ignore the textbook. They'll ask for 2 period lengths. I just want 1. It's pretty easy because you guys can keep going, and I'll show you the shortcuts today. As you go across, there is 4 hash marks going this way. There's always 4. I want to show you today the shortcut for how you find those. Okay, for the sine graph, this sine function, the period length, where one picture completes and then it starts over again, the period or frequency, whatever you want to call it, is traditionally 2 pi. 2 pi, if you don't know, means 360 degrees. That's the traditional like full picture of what the sine graph does. Then after 360 degrees, it repeats, because after a full circle, you would just keep going through the same motions again. You now repeated the distance. So the 4th hash mark down the road is 2 pi. Okay? Does everyone understand that? It's one full picture, ends at 360. Then it will just repeat the picture over. Okay? Now, how I find the hash marks, because I told you what they were yesterday, there's a shortcut, and I didn't tell you it because I want to talk about it today. So, here it is. What you do, you take 2 pi, and to get to this marker right here, I know that's weird, it's the one right in the middle, you cut 2 pi in half.
So it's
1
pi. So it's just pi. So it's 2
pi,
4.
okay? Which is 2 pi over 2. How I get that? It's exactly half the distance. So it's half of 2 pi. Then, to get to the one in front of that, that's again, you take this one and you cut it in half again. So that's pi over 2, right? Because it's half the distance to that marker. And then this last marker that I skipped over, it's 3 times as far from this one. It's 3 of these. These are all the same distances across. They're all 90 degrees from each other. So this marker here, you take the front one and you multiply it by 3. It's 3 pi over 2. Whatever the markers are. Okay, does everyone have the shortcuts? We good? Okay, alright, we're gonna do a couple more examples where I kind of mess with this today. Where, again, whatever this marker is, you cut it in half, you multiply by 3. That's the shortcut. Because again, that's how the distances work.
Why that's very random.
Stop.
No,
Now.
it's just half one and a half two.
Oh, okay. Go one.
Yeah. Alright, now.
Never mind.
For these marks here and here, this is the amplitude number. So again, this right here was period. This is the period length. That's the one picture length, 1 unit. They call it frequency sometimes. The numbers going up and down, this is amplitude. This is how tall your waves are, amp. Traditionally, they always hit 1 and -1. That's the highest and lowest point that a sine graph can go, because if you look at the unit circle, sine will just repeat itself. It's all the decimals between 0 and 1 and 0 and -1. And so sine starts at the origin, it loops up to the first marker, comes back down, loops back to the lowest point, and then goes back up. And it's just a very flowing graph. It's not jagged by any means. There's no sharp edges to it. It's very flowing and smooth. Because, again, it's supposed to represent a circle if you were to place the circle over the origin, and stretch it back together again. But again, this is a wave theory for sine. Now, what we're going to do today is we're going to throw numbers in here for A, B, and C, and we're going to mess with that picture. That's the original picture. Okay, so let's throw a number in there. Let's just mess with the amplitude first. This is always the number I always start with. So we're going to just pick a number. We're going to put it in for A. You can put any number. 5. Okay, we're going to go 5. That was the number I heard. So, all right. So if we go 5 sine of theta, that means the B number is still normal, so that there's no numbering with theta, so that means my period will be this normal same. The 5 is the amplitude number, so A affects amplitude. So I try to label it the same way. Okay, so A affects amplitude.
That's really high amplitude.
Okay, so that means from the origin, from my center, where 0 is at, the origin, we're going to go a total peak of 5 and -5 from that. So really, the only difference in this picture to the normal one is it'll be taller in certain cases. So so this is what the graph will look like. I know this is going to seem silly because I can just draw it over there. I'm going to hit 5 and -5. Okay, but the markers going across haven't changed because I haven't affected the period. I only affected amplitude. So it's going to hit 2 pi, pi over 2, 3 pi over 2. And again, it looks like the same graph. It really doesn't change. And a lot of people are like, well, Ward, why do you even draw it different? My pictures are always very generic. This is the type of picture I would like you to draw tomorrow when you do your homework. You just change the numbers on the graph. You don't need to actually change the look. You don't need to compare it to the original. Because if I actually compare this to the original graph is way, way, way shorter. Now, this is what the original graph would look like. It'd be very small. In fact, I'm going to make it the dashed line. So you can definitely tell the wave is very, very shallow. The only thing we affected was how tall the waves got, the actual amplitude of it. Okay, questions. Now again, if I drew it over here, it would just be really tall, but it would still hit the same zeros, but the amplitude was affected. Now a lot of people are always like, well, Ward, why does it hit the zeros the same? because 0 times 5 is still 0. So it still comes back to the same 0 markers. Okay, the amplitude would affect the peaks and valleys. That's why when you take 1 times 5, it'd be 5 taller. Negative 1 times 5 would be negative 5, so that's why it's lower at that point. So that's why the graph is doing those types of things. Okay, questions?
No.
Okay, so that's amplitude, easy numbers. Second type of thing. So now we're going to affect, instead of amplitude, we're going to plug a number in for B now. And then you can plug any number in here for B. You can use whole numbers, you can use fractions, you can do whatever you want. I can even do fractions out front. We'll do those probably maybe tomorrow. Let's plug a whole number in here for B. Let's go like
231.
2 or 3. Okay, let's do 2.
30.
So we'll do fractions tomorrow. So here we go. So sine of 2 theta. So the 2 is on the inside multiplying on theta. Okay, so how this works, normally, because again, this is going to, again, we're affecting the B number here. That's the number we're affecting. So that's going to affect the period of this graph. So normally, we hit 2 pi. That's normally the fourth marker down the road. What we do is whatever our normal period like this, it's normally 2 pi, you divide by whatever this number is. I don't care if it's a fraction, if it has a weird pi symbol in it, if it's just a decimal, whatever that number is in front of your angle, theta, x, whatever your angle is, you divide by it. So you're going to take that number and divide by whatever it is. Even if it's a fraction, you divide by that fraction. And so this will simplify, so 2 pi over 2 will simplify to be just pi. This is your fourth marker down the road now.
Oh my.
So
It's-
small.
Yeah, so so the length of this thing, the period length now, is actually a little bit shorter. Okay, so if we actually show the graph here compared to the original one, so again, my graphs are always very generic. You know, I have 4 markers going across, the amplitude is 1 and negative 1, so we weren't affecting amplitude here. I didn't put a number out front, you know, so the waves itself were not affected. The fourth marker now is pi.
I asked a question.
So, yep, cut it in half,
Oh my gosh.
cut it in half again, multiply that by 3. Now, how you cut things in half again? The trick is just put a 2 on the bottom. So if you're cutting a pi over 2 in half, you're actually multiplying by half. So you're putting another 2 on the bottom. That's why I get pi over 4. Because again, how I do this. First marker, whatever the period length is, cut it in half, so you put a 2 on the bottom, put another 2 on the bottom, makes 4, and then multiply that first one by 3. That's how I get each marker. Now when you draw it, it's the same thing. It's still a sine function, starts at 0, goes to the tallest point, comes back to 0, goes to the lowest point, comes back to 0. It looks like the same picture. Every picture I will draw will look the same. Like all the scales will look the same. The only thing that's changing is the numbers on my graph. Until you actually compare it to the original. Like if you put them on the same picture, they look very, very different.
What, how did you know that it was 4?
Okay,
What?
this marker right here,
Yeah.
because
No, how did you know that that one was just pi?
pi, okay. It's whatever number they put in front of your theta. That affects your period length. Because normally we go out to 2 pi, 360, right? But if they put a number here, whatever this number is that they put in front, fraction, decimal, whatever it is, you divide your normal period by it. So my period length, one picture length is now pi. If I compare it to the original, and actually what it's doing is, if I were to compare that picture to this one, this is what's happening.
Oh my, that's jagged.
It's actually, and I know it's not perfect, but it's actually, if I were to draw it over the original
Half as
picture,
long.
I would have 2 full pictures by the time the normal one would hit. That's what it's doing. It's shortening up the wave, so I would actually have 2 of them by the time I get to here. Because I completed 1 picture in pi. Pi was halfway across. So, do you see the major differences there when you actually compare them to the original? There is a huge difference. I do not require that you draw the original. I only require you draw the new one. So that's why every picture you will draw in your homework, they'll all look the same. The only thing that will be changing will be the numbers on your graph.
Wait, do we have to draw like that or can we edit the picture?
I want you to draw pictures like that. Like that, not this.
So not
Okay.
a little way.
Not the little one. Yep. Okay. Let's go to the last thing I want to talk about today, which is the shifting, which is the C number now.
Oh gosh, that's gonna be like a nail.
So, so if they plug a number out front, let's say they put like a 4 plus sine of theta. So I'm not messing with amplitude, I'm not messing with the period length because there's no number in with my theta, but the plus 4 means that my graph, my normal picture, is being shifted up 4. It's a normal transformation. It's an actual like translation where it's being shifted. So this is, it's going up 4 because it's a normal translation in like algebra class, where you actually transform the picture. So when I actually look at this, this is how I work with it. I draw my picture, and then what I try to do is before I start putting like the markers and the amplitude and stuff, I figure out where did they shift my picture.
4 out.
It's 4 up, so
That's 4.
1, 2, 3, 4, and I'll keep drawing these up, right? So this is what my normal thing looks like. It's being shifted up 4. This line right here is what I call the origin line now.
Wait, couldn't you just do it how you normally do it and say that 4 is right where you...
Yeah, but I want you to actually show that you're shifting. You could do that, but it gets confusing. It looks like you're over the origin, which you're not. So I'm shifting my picture up 4. What it did is it took where normally my picture is centered right here, now it's centered here, up 4. So if I draw this, I'm going to get rid of all these hash marks here. This is up, this spot is positive 4 up in the air. So I will still go 1 below it and 1 above it.
So that's 5.
So this would be 5 and this would be 3. Because the amplitude number, this number, the number out front,
Just 1.
goes from where your origin line's at. So, you know, if there's a 1, that's normally I go 1 up and 1 down, right? That's what the normal graph does. But it's going from where you shifted. So I will hit 5 and 3 as my lowest and highest numbers. Okay, I still have 4 hash marks going across, as always, but now they're on that new origin line, so I will be hitting 2 pi, pi over 2,
3.
and 3 pi over 2,
Oh yeah.
because I'm not affecting the period on this one. So then my picture goes to the tallest point, comes back to 0, goes to the lowest point, comes back to 0. That's one picture length. It's hitting 5 and 3 as my tallest and lowest numbers.
Wow.
Now, comparing it to the original picture, it looks like the same picture, it's just been moved up. So the original picture wouldn't look any different than that. It's just, this would be just higher on the graph. So if you're on a graphing calculator, maybe you wouldn't see this picture because your graphing calculator would center over the original one. You'd have to like push up and then you'll see it's up in the air somewhere. Okay, now, last example today, I'm going to put all numbers in there. So I'm going to do an amplitude, a period, and a shift
Literally my
on
brain's
it.
gonna be like...
Okay, and I'm just going to go whole numbers today. We'll do fractions and stuff tomorrow so you can see how
Okay,
it
let's
works.
do 3, 5, and 7.
3, 5, and 7, all right.
231.
Those are the numbers we're going with.
3, 5, and 7.
3, 5, and 7. So 3 plus 5 sine 7 theta.
Oh my.
Okay, 3, 5, and 7. Those are the numbers you guys wanted. So what I do first, I figure out where the shift happened. The shift. After I shift it, then I'll figure out where the amplitude will go, because obviously my amplitude will be 5 from the new origin line.
So that's gonna be 8.
And then the 7 will affect the 4 hash marks going across. That's how it works. So, all right, here we go. Okay, this is my last example of the day, then I'll give you time to work on your homework.
L fixer?
Just remember.
All right, so here's my graph. I'm being shifted up 3. Okay, so there's my 3. And then from this spot, this is my new origin line.
Go on 5.
Yeah, I'll be hitting 5 up here. Now I'm going to draw this very bad, but I'm going to hit 5 up here. So that means up here, 1, 2, 3, 4, 5. I'm going to be hitting 8. That'll be my highest point. It's going to be 5 from the origin line.
Holy.
So if this is the new origin, right, that's my C number, this is the amplitude number. So it's 5 from that. And then that means I have to go 5 down from
So
there.
-2.
So I'll hit -2. That'll be my highest and lowest point from the origin.
Holy wavelength.
Now, why it's those numbers? Because you have to go 5 from the center. That's the tallest and lowest points of the waves. Now, the 4 hash marks going across, now I know my picture looks terrible, just go with it. The 4 hash marks going across. Normally, I would hit 2 pi, that's like the 4th hash mark down the road, it's 360, but we have to divide by 7.
That is.
Because that number, when I divide by 7, that's the number where the 4th hash mark is going to be. So this is 2 pi over 7. Now, when I cut that in half again, you put a 2 on the bottom, that's pi over 7. It would be 2 pi over 14, right, if I put a 2 on the bottom, but you'd simplify. Then I would divide this by 2 again, which would be pi over 14 now, because you put a 2 on the bottom, and multiply that by 3. 3 pi over 14. That's why I've been teaching these shortcuts. You take whatever your number is, you cut in half, multiply by 3.
I like this.
And now when I draw, we start on the origin, we go to the tallest point, we come back to the origin, we go to the lowest point, which is not on the scale, and here you go. It's a terrible drawing.
You hit that point. That's like a.
There you go.
Wait, how come you always go to the top one? Why don't you go down first?
That would be if we were to ever mess with the graph, like throw negatives in there, if we were to do other trig functions because they have their own look when we draw the other ones. But this is the normal traditional graph. Now, as I said before, you know, this can be used for oceanic studies for waves, it's used for sound, light, they have their own types of waves. So I'm going to show you my little 1-minute clip of the guitar strings. This is a local, not a local artist, but an artist that I found on YouTube that I really like because I like his artistic shots that he does with his guitar, and he's actually a really good musician. So,
Make sure to turn it off. We don't want you to get in trouble.
Michael Big stuff.